Hello, this is Dr. Vev. I would like to discuss an example of contour integration where the contour is not a semicircle or a circle. Consider the following integral. It is actually related to the double gamma function identity. So for those who are interested, you can try to find out the connection on your own. Here, I'm more interested in simply working out the integral, that is to say, proving this identity. As always, we complexify our integral, so let's consider the integral in the complex plane instead. So I replace the x by z, where z equals x plus iy. Now, this can be written for convenience as f of z dz, where f of z is the function e to the az divided by 1 plus e to the z. Now, this function will cease to be analytic when the denominator is 0. So let's try to find out when that will happen. Setting the denominator equal to 0 gives me 1 plus e to the z is equal to 0. So you might think that it happens when e to the z equals minus 1. An immediate root is e to the I pi. So you may think that z equals I pi is one solution, but that's not just one solution. We have to add 2n pi times I to that, because e to the 2n pi I is equal to 1. So these are the solutions for n in the integers, positive or negative. We can solve for z. This gives me z equals I pi times 1 plus 2n. 1 plus 2n are odd numbers. So we're going to have things like plus or minus I pi. The minus sign comes from considering negative values of n, because n can be both positive and negative. Plus or minus 3i pi and so on. Because you have an infinite supply of simple poles, strung along the positive and negative imaginary axis, you can no longer take a circular contour. Because if you take a semicircular contour, you'll simply end up embracing more and more of these poles as you go out. So you can't make the semicircle argument that things vanish on the semicircle, because there's always going to be a pole present along the y-axis. So the way around this is to choose a rectangular contour. That's what we're going to be drawing here. So I'll draw my real and imaginary axes. So here's your first pole I pi, and the corresponding negative I pi. Then I have 3i pi, and so on that side and this side. But if we choose a contour that is something like this, now for convenience, I take the contour to go through 2i pi. That's not necessary. And a good exercise, in fact, for you to would be to take this at some value between I pi and 3i pi and show that you get the same results as in this video. So let's just consider a rectangle of width 2r along the real axis. And let's consider the path to be counterclockwise. That's usually the case with complex integrals. Now we can write the overall integral that we have, I, which is over there, as a sum over all the over the top, over the bottom, left, and the right of this rectangular contour of f of z dz. So I've broken it up into 4 integrals. My next aim is to show that each of these is 0 separately. Then we'll just be left with the top and the bottom, and we can deal with that in an easy way. Now when I say it goes to 0, I mean as r goes to infinity. So keep that in mind. It's not 0 as written. As written, it's going to be some finite value, but as r goes to infinity, then it goes to 0. Let's consider in detail the right side. So the integral on the right side, f of z dz, is going to be the integral from r to r plus 2 pi I of e to the az divided by 1 plus e to the z dz. What I'm going to do is parameterize the complex number, because the complex numbers are forced to lie on the vertical line. So I'm going to create the equation of a vertical line. That equation is r plus iy. This means the real part is fixed at r and the imaginary part is free to wander up and down. So that's the vertical line parameterization. And once I have that, I can differentiate both sides. So I get dz equals I dy. Because r is a constant, you don't get any contribution from that. And the limits, instead of going from r to r plus 2 pi I, the limits would be on y. Y will go from 0 to 2 pi. Now, I'm interested in estimating the right hand side. So what I'll do is I'll take the absolute value of the integral f dz. Now for convenience, when I write f dz, I mean f of z dz, and when I write f dx, I mean f of x dx, just to make things easy to write. So that's going to be the absolute value of the integral from 0 to 2 pi e to the az. For z, I'm going to put r plus iy, so I'm going to get ar times e to the aiy using the property of exponentials. And then here, likewise, e to the r times e to the iy, and dz is I dy, the whole thing absolute value. By the Cauchy-Schwarz inequality, this is going to be less than or equal to 0 to 2 pi, the absolute value of everything inside. There's no real need to put absolute value around dy because y is positive, but I just did it anyway. This is from the famous inequality of Cauchy and Schwarz. Once we have that, that less than or equal to sign, once I put that, every other step following that will also have the less than or equal to sign with respect to the left hand side, but I won't write it. So the integral, so this is equal to the integral from 0 to 2 pi. The absolute value of e to the I theta is just 1 because it's just a complex unit circle. So that'll be 1, that'll be 1. The absolute value of I, well, if you think about it, the absolute value of I is just the absolute value of e to the I pi by 2, and that's also 1. So the absolute value of e to the I theta in general equals 1. So all those things will just disappear, and I just end up getting e to the absolute value of a, because you should consider the absolute value of a there. We don't know if a is positive or negative. R divided by 1 plus e to the r times dy. This can be integrated because I don't have any dependence on y in this integral. So I can take out the whole stuff, and then the integral is just 2 pi. So this is just going to be 2 pi times e to the absolute value of a times r divided by 1 plus e to the r. Now what I'm interested in doing is estimating. So I take the limit as r goes to infinity of the absolute value of f dz on the right. Well, that's just going to be 2 pi times the limit as r goes to infinity of this quantity here, e to the absolute value of a times r divided by 1 plus e to the r. You will notice that the limit is of the form infinity by infinity. So we can use L'Hopital's rule. So I'm going to get 2 pi. L'Hopital's rule means you can continue by evaluating the limit of the derivative of the numerator divided by the derivative of the denominator. When I take the derivative of the numerator, I pick up an absolute value of a times the limit as r goes to infinity e to the ar, because the exponential function, when differentiated, gives you back the exponential function. Denominator, the 1 disappears, and I simply get e to the r. Now that's a interesting statement that can be written as 2 pi times the absolute value of a times the limit as r goes to infinity. What I'm going to do is I'm going to bring the e to the minus r from the denominator up to the numerator. So when I do that, I'm going to get e to the absolute value of a minus 1 times r. Now immediately you can see the reason the problem was stated with the following condition, that the absolute value of a be less than 1. Because what will happen if the absolute value of a is bigger than 1 is that this contribution will simply blow up, and we are stuck. We can't go any further with this contour integration. So what we can do is, because we are aware of that condition that was given to us, we can write this as e to the negative 1 minus absolute value of a times r. And since absolute value of a is less than 1 by the condition in the problem, 1 minus absolute value of a is always positive. So this is a positive quantity times r, which is positive. And so the e to the minus a positive quantity, where the positive quantity goes to 0, is in fact 0. So in this manner, we have shown that the contribution from the right branch is 0. Now, rather than go through the same computation on the left side, which will considerably increase the length of this video, I will set that as an exercise for you. So here's a little exercise for the dedicated watcher of this video. The second integral I will not do. I'll tell you what answer you're supposed to get. The absolute value of the contribution on the left, f dz, will turn out to be less than or equal to e to the minus absolute value of a times r, 2 pi, divided by 1 minus e to the minus r. And that limit, as r goes to infinity, of that thing will be 0, exactly as we did for that. So now we only have to worry about the top and the bottom part. Let's talk about the top. The integral on the top, f dz. Well, that's going to be the integral from r plus 2 pi I to negative r plus 2 pi I. I want to remind you of the contour here. the top goes from r plus 2 pi I all the way down to negative r plus 2 pi I. So it's actually going in the negative direction. So you can expect the answer to be negative. Integral e to the az over 1 plus e to the z dz. This time, the parameterization we're going to have is for the horizontal line. So let's use the parameterization z equals x plus 2 pi I. When you differentiate this, I get dz equals dx, and the limits are x from r to minus r, because it starts from the right and ends up in the left. Let us find out the value. So this is going to be, let's just take the limit as r goes to infinity, because that's important. Without that, you will not lose the left and the right sides. So we have to do that from now onwards. Top f dz, that's going to be equal to the limit as r goes to infinity, the integral from r to minus r e to the ax times e to the 2 pi I a divided by 1 plus e to the x times e to the 2 pi I, the whole thing dx. Well, e to the 2 pi I is just 1. And when I take the limit as r goes to infinity, I just get plus infinity on the here and a minus infinity there. So that's e to the ax, e to the 2 pi I a divided by 1 plus e to the x dx. What I will now do is insert a negative sign and then switch the order of the limits. And I'll take out this term because it's a constant. So negative e to the 2 pi I a times the integral from negative infinity to positive infinity f of x dx. Let us save that. That's as far as we can take that. Let's finally go to the last contribution, and that's the bottom. What's the bottom contribution going to look like? That's the fourth integral. Well, the integral on the bottom, f dz, is rather simple. There, I'm going from negative r to positive r, and the value of y is 0, so I'll simply get e to the ax over 1 plus e to the x, and dz just becomes dx because dy is 0. So that's just equal to that. And in the limit, as r goes to infinity, which we need to lose the left and the right sides, I get negative infinity to infinity e to the ax. So this becomes 1 plus e to the x dx. So now the total integral can be written down. Therefore, the total integral I, which is the sum of the four integrals over the rectangular contour C, f dz, is just 1 minus e to the 2 pi I a integral minus infinity to infinity f of x dx. But the integral over a closed contour by the famous theorem of Cauchy and Gorsa is 2 pi I sum over the interior of the contour of the residues of the function. And this is by Cauchy residue theorem. All we now need to do is calculate the residue of the function f. And here I would like to quote a result in the form of a lemma. So the lemma is as follows. You can find the proof of this lemma anywhere. If you have a function f that can be written as the quotient of two functions g and h, and h at some value z naught is a simple pole, and at that same value g is analytic, which means it satisfies the Cauchy-Riemann conditions, then the residue at that value z naught is given by g of z naught divided by the derivative h prime evaluated at z naught. So that's the result that we're going to be using. In our case, g of z is the numerator, which is e to the az, and this is an analytic function in all of the complex plane, and our function h is 1 plus e to the z, whose derivative h prime required for this formula is just e to the z. So the residue at the simple pole z naught, in this case is I times pi, which is inside the contour, our rectangular contour, is just going to be the value of g, which is e to the I pi a, divided by the derivative evaluated at the same point. So that's going to be e to the I pi. Well, e to the I pi is cosine I pi plus I sine pi. Cosine I pi is -1, so that's going to be negative e to the I pi a. So we are ready to put everything together and finish our calculation to find the value of the integral. So this is a great moment. All our work will finally be put together. So the integral I, which is all of that, 1 minus e to the 2 pi I a times the integral from minus infinity to infinity f of x dx is 2 pi I times the sum of the residues, which is this one. So I get a minus from this minus sign, 2 pi I times e to the I pi a. Okay, now all I have to do is evaluate the integral. So that gives me the integral minus infinity to infinity f of x dx is just equal to negative 2 pi I e to the I pi a divided by 1 minus this thing here, e to the 2 pi I a. Now all I have to do is bring that minus sign inside. If I do that, I can interchange the order bit of these two terms. So I can write the integral minus infinity to infinity f dx is equal to, I'll take a pi times 2i e to the I pi a, and then I'll interchange the two terms to absorb the negative sign there. So I'm going to get e to the 2 pi I a minus 1. Now all I have to do is divide both sides by, or multiply both sides by e to the minus I pi a. When I do that, this disappears. So I'm going to get pi times 2i. And when I multiply the denominator by e to the minus I pi a, the first term becomes e to the pi I a, and the second term becomes e to the minus pi I a. Well, do you recognize this? That's just pi over sine a pi, because the sine of anything is e to the I theta minus e to the minus I theta divided by 2i. So that's just the reciprocal of that, where theta equals a times pi. Beautiful. We have proved this important and amazing integral. This is related, as I mentioned in the beginning of the video, to the identity involving gamma functions. So you must try to investigate the connection between the gamma function identity, which is gamma p times gamma 1 minus p, is pi over sine p pi. In other words, you have to show that the product of these two gamma functions can be written as the integral we started with. I leave that as a exercise for the students watching this.